So welcome to the third class in this SAGE and Programming and Eventually Algebraic Combinatorics course here at IMSC Chennai. You can see that today we have the advanced programming tutorial, by which I actually mean the second introductory tutorial, but we can say advanced because it's more unusual topics. As always, these are based on tutorials created for a National Science Foundation funded workshop, so I have to acknowledge that, but I really enjoy this one because now we get into some stuff that's a little bit deeper. But before we do that, I'm going to just briefly talk about the homework. And for those watching online, this video may be a little longer than the other ones, and for those in the classroom, we may go a little bit past 11:30. I hope that we will survive. So some of these things are not things that I want to discuss right away from the homework. The string stuff is not really that important for number theory purposes or anything else. But I hope that people at least are able to pick a type of object and try and do something to it, right? So whatever your favorite thing is, if it's a group, if it's a number field, graph, just can you do something to it, and can you then write a function that does something to it? That's a really important thing to be able to do. So I hope everybody was able to do that. Did everybody figure out how to get a block diagonal matrix? Yeah? What was the command? Block underscore diagonal underscore matrix. Seems kind of reasonable, right? So these are the kind of things that if you just do a little bit of a search within the SAGE documentation or even online, you should be able to find that. Sometimes it might have been diagonal underscore block, or something. So you just have to be careful about things like that. But in general, it's not so bad. Some of these other ones, I'm happy to meet with you afterwards to see if you did pretty well. This Project Euler problem number 6. This one, I think I just want to ask about very briefly. The difference between the sums of the squares of the first 100 natural numbers and the square of the sum. So of course there are formulas for these things, right? So you could have used that, right? But did anybody figure out how would you get the sum of the squares just using SAGE? What would you do? Could you use a list comprehension for that? Yeah. Or a for loop, yep. Great, yeah, sure. You could start with something like let a equal 0, and then you could say for I in 1 to 100, a equals a plus I squared, something like that. That would be fine, right? So there's lots of different ways to do it. And the point is just to know that these are things that if you go slowly and try small examples, like can you do, instead of 1 through 100, can you do with a 1 through 10 squared? Can you do that one? And so that's the kind of thing I just want you to think about. The loop, I would have used a list comprehension and then put the list inside of the sum function. And that also works, okay? There are many ways to solve these. Python does like to make it so that there's only one way to solve things, but it can't help itself, and sometimes there's more than one way to solve things. So anyway, this reading about deep copy, this was certainly one of the more bonus problems, as I said, but I hope that at least it got you thinking about why copying would be important, even if you didn't understand the copy. And then did you figure out how to write a function, which depending on the input takes a number and squares it? Or it takes, so we have, now Dilpreet has all the answers. Is there somebody else? So she's A+ student so far. Then Biswajit? Yeah? So what did you do? Huh? Yeah, tell me what you did.
Definition.
Yep, def.
Just one.
He's finding it. Let's call it F.
Yeah.
He's finding it. X, comma. Oh, we need a colon? We need more than that. We need 2 arguments, right? Yep, and then I think we need y equals something, right? Equals 2, very good. Why is it y equals 2? Because the squaring is going to be our default, right? And then let's take a number and square it. Well, x to the y. Very good. Actually, I forgot that, so I would have had error. It would have just computed x to the y and then stopped, but it wouldn't have returned it. It would have just computed it internally, and I would have never known. So that's a very subtle kind of bug. All right, there you go. So now f of 3 is 9, and f of 3 comma 3 is 27. Okay. So you can actually do this stuff, and I hope that those who didn't do the homework will not cheat and look at this. All right, do your own homework. Okay. All right, does that get you kind of back into the flavor of things? Right, we're trying to do some simple things. It does take time, but eventually you can really figure out what you want to do with some of these things. Now, as I pointed out, this is supposedly the advanced tutorial, but of course it's really just this second introductory tutorial. You could spend weeks and weeks on useful programming techniques, and later on there'll be the object-oriented piece of the structure. But there are some things that I think are going to be really useful right away, particularly for the research group, and so I'm focusing on some of those and trying to think of ways that are just a little more advanced than I would in a typical tutorial series, which would be more focused on just learning more about how to do calculus or something. So this is kind of a potpourri of a lot of useful ideas. This is not a comprehensive list at all. So structure. We're going to talk about structure and flow a little bit, and this will answer several questions that people had actually just as class was coming together. Remember last time, we saw it with the definition that we just got. Biswajit and Delpreet helped us out. We had this indentation thing. And so we saw this block structure last time. So here's another example. So here's one way to get a quaternion group. Many, many groups and graphs and matrices are built into Sage, kind of common ones that you might use. So here we're going to take the quaternion group, just the regular quaternion group. And we're going to then start with an empty list, just like we did before, and then we'll append each subgroup of the quaternion group. And you can see there's a lot of subgroups of the quaternion group. And this is the way the generators are done in Sage. They consider the quaternion group as a subgroup of the symmetric group on 8 elements. Okay, so that's kind of how they represent it, because that's kind of one canonical way, I guess. So I got all the different subgroups. Okay, so that's fine. But what if I want something more interesting? Oops, where'd it go? If I want something more interesting, I'm going to have to be a little bit more subtle. So for instance, what if I want 2 random elements of each subgroup of the quaternions, and then that's like as always one big list? Okay? So you might want something like that. So let's take a look. First, I'm going to reset L back to the empty list. And then I'm going to do the 4 G and G dot subgroups. So I'm going to go through all the subgroups again. But now I'm going to do a nested operation. I'm going to do inside of this indentation, I'm going to do another thing, another loop for I in range 2. What's range 2 again? 0 and 1, right, exactly. Right? It's not 1 and 2, it's 0 and 1. So for 0 and 1, and that's just counting through things. There's nothing magical about that because I don't use the I here. It's just a way to count twice. Append to my list G dot random underscore element. Okay, so unsurprisingly, that's a random element. I don't know how it's implemented. I don't know how random it truly is, but it's random enough for today. Unsurprisingly, in the trivial subgroup, both random elements are the same. Okay, that hopefully that's supposed to be funny. Huh. Trivial subgroup, random element. Come on, right? And then we get some other ones. We see the bigger the groups get, then the less likely it is that we get the trivial element. But it's this nested indentation. Now look, here I still have the 4, I still have the colon, and I have to do another 4 spaces, or whatever I'm choosing as my indentation. So I'm doing the same thing twice. Now once you start thinking about it, of course this is not so hard. Like it's a pattern, right? So this is what we do as mathematicians. But the first time you see it, you might think, oh my goodness, I have to go and like indent, indent, indent. So you have to be careful about how you put it together. But this is, you can think of this as a prototype for how to do this. Also notice one extra thing. There's this sharp or hashtag. This is actually called an Octothorpe. That's the technical name for it. And this has a comment. So you see that this didn't show up down here. That's because everything after this comment is just ignored. But it's useful for humans to read, right? It's a useful comment that I said, oh, don't forget to reset L. Oh my goodness. I don't want to keep adding things to L. That was what happened last time. I think Uda pointed that out. And so that's telling me something. But the main point is this nested indentation. I would like to ask if you understand it, but I'm assuming you don't yet, so we're going to see a couple more examples. Okay?
So you're creating one list with 2 random elements from each sub?
Yes, that's correct. Well, yeah, I mean, it's not that useful. You're going to see why in just a second. Okay? The reason is because it's actually kind of tricky to create a list of lists. So here's one way to get a list of lists. That's if whatever you're doing your first loop on has a list method. That makes it easy, because now I didn't have to do another loop. So for G and subgroups, append the whole list of all the elements. So that one actually will give you the whole list. Okay, so there's all the elements, and you can see that they're demarcated, right? Here's the list of all the elements of the trivial subgroup. Here's the list of all the elements of this subgroup of order 2. There's 2 of them. And then the other subgroups have a lot more stuff in them. And the last subgroup has all the elements, because it's the whole group. Okay? Now, what if I wanted to truly get another list? What I'm actually going to do then is I'm going to use a list comprehension. It's just too tricky to try and do it in 2 loops. So instead, I do my loop. And then inside the loop, what am I going to append to the list? I append this whole list. And remember this notation? It's like the set builder notation in math. The order of the element for every element in the group, or in the subgroup, I guess. So I'm going to have the order of each element for each element in the group, and there it is. So again, trivial subgroup, there's only 1 element, order 1. There's 2 elements in this subgroup of order 1 and 2. And then most of the other subgroups will have 2 elements of order 4, 1 of 2, and then 1 of 1. And then, of course, the last subgroup will have a whole bunch of elements. So there's a few different ways to create a list of lists, but you do have to be kind of careful. So that's the kind of thing you just have to kind of do on a case-by-case basis. Now, this block structure is important for many reasons. Everything in Python has this block structure. We just saw it with the defining of the function. We saw it with the loops. And now we're going to see it with something that a lot of you were wondering about before class started, which is, what if I want to do something? What if I want to only pick out certain elements? That seems like a very reasonable thing to do. I don't want every single graph. I don't want every single group. So here, I'm going to actually pick out every element of the quaternions, which has order 4. Okay? There's no elements of order 8, so that would be a silly thing to do. So for G and G, and then notice I have a comment, right? That sharp sign or hashtag, if you guys are on Twitter. If G.order, if the order of G is 4, print G. And so if we go back up, there they are, okay? And of course, there are 6, as we saw earlier, right? A couple elements of the Quaternion group do not have order 4. Yes, and that is exactly right. That is one of the really important things I just wanted to point out, and it's right off the screen. I have to use the double equals sign. And the reason I have to use double equals is because the equals already means something. We just saw above, and the last couple days, that equals means name a variable. So if I said G.order equals 4, I would say, make the order of every element equal to 4. And that's not a group, right? There is no such thing as a group where every element has order 4. So I say if it double equals signs 4. So this is the comparison operator. There are many comparison operators, and I have a little, I have a little list of them here. Sorry, again, not my computer. Don't blame me. There's a link that I have here into how Python compares elements. Not equal to, greater than or equal to. It's very important to read for the mathematical crowd. So I think that that's really a good thing to think about, is how that would work. In a longer course, you'd do a lot more with it. We can't do more with it here. But it is important that that's how we compare two elements. Well, once I've compared them, if the order of the element is 4, then I'll print it. And that's what this notation means. If something happens, colon, indentation, so extra indentation in this case, print it. And it does. So there's the loop, and inside the loop I'm checking whether or not this is true. If it's true, it prints, or whatever is below here happens. And if it's not true, you just go on to the next guy. Okay? So this is called a control statement, I believe is the technical framing for that. I'm not a computer scientist. But let's see. OK, here's another example. Okay? So this is nice because I'm abusing notation. Right? I have this matrix. So this is a definitely singular matrix, because the last row is all zeros. And then I have all the integers from 0 to 4. I'm going to look at the powers. We did this last time, right? We took powers of matrices. And I say if, again, it's already indented. This is already what happens in the loop. And then I put the thing I want to do indented again. So if the power of the ith power of the matrix is equals, so really is equal to, comparison, 0. Powers of matrices aren't 0. They're 0 matrices. Okay, but Sage knows. Okay, Sage knows that that's what you meant. Because there's really no ambiguity. It is abusive notation, but it isn't really. So if it is the 0 matrix, comment, because I'm going to show it to my students or collaborators and they're stupid. And then it's going to print it. And as you can see, there's only one power that I checked where the matrix's power is 0, which is the 4th power. If I change this and went to 6, I bet I'd get a couple things. Right, okay, so now I get 4 and 5. Okay. So it does exactly what I want it to. The way to learn how to do this is to actually try it out. So again, earlier people were saying, like, what if I wanted to get a list of all the graphs of order 5? The graphs that had the 6 vertices and 5 edges or something like that. So now I can use this if to do that, okay? Rather than using some built-in property of the graphs object in Sage. Well, there's even more blocks that Sage has, or Python has, and I don't have time to spend a lot of time on them. So instead, as part of your homework, you're going to learn what these blocks mean. So do your homework over the weekend. Online people, you do your homework too. So I have here 2-part blocks. So if here's an if. If the length of f equals 1, then I'll do something, I print something. And if otherwise, I print something else. So there's 2 things. They both have the same indentation. And then inside of them, there's stuff that's indented further. And you can probably guess, if this happens, print this. Else means otherwise. Okay? This try except is a little bit trickier. But I really want you to think about that. Because as programmers, not simply users of Sage, but potential contributors, learning how to deal with errors is actually very valuable. Okay, so here's what happens. Right? You didn't try to factor 0, did you? But then I also, somehow magically, all the numbers appear. How did that happen? So that's yet another thing for you to check in your homework. So this is a much more advanced example, but I trust that you guys will be able to figure it out by slowly taking it apart and looking at each piece, okay, and looking at what the structure is. Remember, structure is everything in math, and in Python, the structure is the colons and these indentations and how far in they go. Okay?
Now, are you free to indent things as you wish if there are no colons?
No. No, indentation, I mean, white space is meaningful, so you have to be very careful. Yeah. You'll usually get some kind of indentation error.
But you could have new lines, right? I mean,
Yeah. New lines are fine. No, it's only white space, not new lines.
We're defining a matrix out.
Yeah, that's fine. Yeah, that's no problem. Yeah. Yeah. Now this is your homework, so I'm not explaining all of this, right? But
so the dot format is something that so that can be used for any object.
So that's one of the things, and I give you a couple links for this. So this is how to format strings. It is the technical word. All you have to think of it as, how do I get it to print out the number that I was trying to factor? But what it does is it's a way to put things, it's a way to make it so that if you don't know ahead of time what's going to go into words, then you can make the words go in. So 2, 3, 4, 5 went in.
So there's also this thing with percentage %s.
Yes, I'm using this because this is the modern. This is the modern version. Yeah.
Someone over told me about this.
No, but because it's new. I mean, relatively new. Okay, now we're going to spend a lot of time on lists and their friends. We're going to introduce some new data structures today. There's quite a bit to do. So let's review a couple things from last time. So here's something that was in the homework, or implied by the homework anyway. I asked, what is this a with a -1 in the brackets? I think most of you figured it out in class last time. It's if you count backwards. So instead of starting with 0, 1, 2, -1 starts at the end. Okay, so it's the last element. If I did a -2, I would get this element because I'm going backwards. The second to last element. So this is last element. -2 would be the second to last element if there is one, and so forth. Okay. Now that should have been clear from the homework, but what's interesting is that I can change elements with this notation too. So I had 1, 2, 3. Now I have 1, -1, 3. So what you can do is you can use the equals sign with this bracket notation to change a list. Very useful, right? So you start off with some default, right? And then you say, but I actually want to look at this variation on the object, right? So think of it as a deformation, maybe. You put in a couple epsilons, and all of a sudden you have something different. So I changed 1, 2, 3 to 1, minus 1, 3 with a pretty simple notation. I didn't have to do anything different. And this is still the same list. And it's still called A. So you'll see why that's important later, I think. But it's just really nice that you can do that because, well, why wouldn't you want to be able to change things easily? Some of you might know some programming, and you might have learned a language where you can do this, but you can't. And Python doesn't allow this. You can't make a list longer by using this notation. You have to use the append or some other, there's some other things you can do, concatenation. Okay. Now, that seems OK, but let's actually do something more interesting with it. So let's take all the numbers from 0 to 9, and let's get a bunch of them. This is called slicing. So what I can do is I can actually get a bunch of elements of the list. Notice, again, just like with range 10, where does it go? It goes up to 9, right? With slicing from 1, 4, I get 1, 2, and 3. Again, the last element is not used. Okay? It's just this thing about Python. I didn't invent it. Not my fault. So you can say this notation is short for the ith slice for I equals 1 less than 4. So if I wanted to have a big list of stuff, let's say I computed a whole bunch of, I don't know, group cohomologies or something, and I only want some of them that I want to process. OK, I can just slice my list, and my original list is still there, but I'm only going to deal with the ones that I care about. So I'm just processing some of the list. Very common, typical thing to do. Right? You only want to look at the ones that you care about. It turns out this is very powerful, though, because there's a lot of defaults. So if I want to get everything up to 4, but not including it, or everything from 4 and up, I can use this notation. So the colon is very versatile and flexible. And I can even assign things to a list. So let's go back just a second and see what was the list A. OK, it's 0 through 9. Everybody got that? 0 through 9 in order. Right? Now, let's see what happens if I use this notation to assign something. Oh, now I get 0, 2, 3, 4, and then 4 through 9. So I changed the elements 1 through 3 by using this notation. Really cool, really slick. So it's a really easy way to do this. Now, if I don't use the equal sign, though, it's just a copy of the list. So here I actually changed the list because I used the equal sign. But this thing up here is not the list A. A remains unchanged. I didn't like slice A. Has anybody ever taken a PDF file and then you've tried to crop it to just get like a, your favorite person's picture, because you want to, I don't know, put it on your Facebook profile or something, right? And then there's this warning that comes up. Warning, cropping a PDF file does not make it smaller. Has anybody seen that? OK, some people know what I'm talking about. So that's what's going on here. It doesn't actually change A. This changes A because I did the equals. So if I want a copy of the whole list, well, default is beginning and end. So I get the whole thing if I do this notation. It's very weird notation, I have to admit. So if you just saw this for the first time ever, you're like, what the heck is that? But you'll actually see this in Sage Code a lot because you want to make a copy of a list and you want to do it as easily as possible. And so this is actually a really slick way of doing it. So now you know if you ever see this in the Sage code base, this is what it means.
It's equivalent to saying copy A, right?
I don't know. I'm not sure if it's technically, I mean, functionally it's probably equivalent. But I don't actually know internally in the computer if there's a difference. There may be. There may actually be a difference. Yeah, I couldn't tell you. But functionally, yeah, I mean, it does what you want. It saves a couple keystrokes.
But it's better to be clear than to be clever, right?
Depends. Yeah, I don't know.
So if you assign it to another,
Yeah.
it should be.
Yes, exactly. And then you won't have the problems with copy and deep copy. That's right. Right. Well, yeah, you might still have the problems with deep copy, but you won't have the problems with copy. So, OK, here's another variant on the syntax, and I'm just going to do a bunch of these.
So just a sec. So if you're,
Yeah.
if it's just a list of numbers, there's no point in deep copying it, right? You just copy.
No, I don't think so. Yeah. So here's even more variants on this syntax. This is more advanced, but you can see that here I wanted only the skipping by 2, and there's a 2. Here I skipped by -1, so it started at the end. Here started at 3, -2. You have to figure out what that -2 is, and then the skipping by 2. So one of your homework exercises is to figure out exactly what is going on here, and to write up a specification of when there's 2 colons, what happens. But I think you can already see, by looking at where the placement is inside the colons, what happens. So like this -3, what does that -3 mean? Going backwards, or the third element from the end, right? Okay, and so then, and then it went to the end. So some of the other ones are a little more complicated, but you can figure them out. And so that's one of the homework exercises. It's you can write a formula. You really can write a formula. So it's very nice. And it's a linear formula, just so you know, okay? No, nothing crazy. Now, this is great because matrices slice too. Sage has adopted this notation for its matrices. In fact, Python is now adding matrix slicing notation, which is different from Sage's slicing notation. That's kind of annoying. But whatever, we've had it for years. So here's a matrix, and I used a little bit of a slick thing here. Instead of putting the list in, I said this is a 4-row matrix, and then the numbers are 0 through 15. So there's many ways to construct matrices, and you should familiarize yourself with that if you're going to be using matrices. So modular forms, I guess they use a lot of matrices to represent them, right? So you got to know all about matrices. So now I can use this slicing notation. So here's 2 different things that I can do with this. Here we go. So in this one, I got every other row. That's what this is going to mean. Columns 0 and 3. So the rows are before the comma, and the columns are after. So let's check. I got the 0th row and the second. No, what did I do? Oh, columns. Right. Column 0 and 3. Column 0, column 3, and then the top row and the third row. Yeah, that's what I got. 0, 3, 8, 11. That's what I got. Now, I'm going to do the same thing, but I'm going to use the equal sign to set that. I'm going to set those spots to -1, 2, 0, and 0. Let's see if it worked. 0 became, everybody? Everybody? Yes. -1. You guys are, come on, let's go. 3 became 2, yeah? And then there's the 2 extra zeros. Interaction. Okay, so the point is that I can do a lot of very powerful things with matrices by using the same slicing notation. And that's much more useful, I think you might think. And so again, I'm not going to explain all of these examples. This is nice, right? I reverse the rows, but not the elements in each row. In this one, I get just the last row, and then the first row with columns 1 and 2. So I can actually change the order of them. So I can do pretty arbitrary stuff with this notation. Now, it's dense notation, granted. So if you actually use matrices, I don't really use them in my own research, so I'm not, and I don't teach linear algebra very often, so I don't need this notation very much. But if you do, if you're doing permutations of things, or like even for some statistical tests, you have to do permutations of the rows of data, then this could be very useful. So slicing, again, really nice, really useful, fun topic, I think. I mean, it's kind of fun to be clever in how you use the fewest number of keystrokes to do something. And mathematicians love clever proofs, right? Now, slicing can go just one way sometimes. I didn't talk about this homework problem because I was going to talk about it here. Did everybody figure this one out? If you take a numerical integral, it gives you the answer and the bound. To get just the answer, you slice it, you take the 0 component of it. Did everybody get that? Or everybody who did the homework? Yeah? So that makes sense, right? It's the 0th term. So now, because this is the thing separated by commas, and there's the 0, you might think, hey, I can change it. I can change the answer of my numerical integral, right? I mean, not really. But I can at least change the ants. I can change the thing. But I can't. Type error. Tuple object does not support item assignment. What the heck does that mean? Well, what's going on here is that when Python functions return things, if they return more than one thing, they return them as what's called a tuple. It's something like a list, but you can't reassign. It will not change. So you don't have to worry about copying kind of issues because you can't change it, right? There's nothing you could ever do to make it different. And that's useful because sometimes you don't want to accidentally modify stuff. You want to protect yourself. Imagine that you're doing this really long program, and then for some reason, you accidentally make it so that you change some item. And then you never notice this bug until there's some really weird subcase that it's crucial for proving the theorem works for n equals 10 instead of n less than 10. And then because you did this, it makes it wrong. That would be terrible. So whenever you have a tuple, you cannot change the things. Now what is a tuple? A tuple is just like a list, except it's defined by commas. If you want to, you can put parentheses, and most people do. But it's the commas that actually define it. I recommend using the parentheses for clarity. And it's printed out using parentheses as well. And indeed, now I cannot change it. Okay? So here's a link to what things you might want to do with tuples. But the most common thing you might do with a tuple is that if a function returns more than one thing, they will come in that way. And then you might want to assign them to other names. And so that's what I'm doing here. I assign the output from numerical integral as answer and error bound, and then I print the answer and print the error bound. And of course, what I could do then is I could format those things nicely, right, for a paper perhaps. I could format the answer, format the error bound, using exponential notation or something like that. Or there's lots of things that I might want to do with that. So that's the primary thing that you might do with a tuple, to me. There are other reasons you might use it, but you'll have to ask the people at the Sage Days next week where they use them, because I don't use them that much myself, other than this kind of situation. Whew, okay, let's take a quick break. Everybody, think about all the different kinds of things you can slice. I can slice lists. I can slice matrices. I can slice these tuple thingies. Okay, a lot of tuples. Question?
Can you slice this and lose them?
Yeah, I can slice them. I just can't assign. So that's what I did here. The answer, ANS, is the numerical integral error bound, or the answer and the bound. And then when I sliced with ANS 0, I got the 0th element. But I can't assign things with it. So I can't change ANS by using this notation. I can only get it. I can't set it. And that's good because you might sometimes write a program where you don't want anybody to mess with something. You want it to be in there so that somebody can't accidentally change it. Does that make sense? Yeah? Okay. Again, you can always watch the lectures again later or read the many Python tutorials on the internet, and probably in your library as well. Okay, so that was a break. But we need a break because we're just constructing lots of things today. So even more data structures. And again, these are all really important. Okay, I'm not making up that these are useful for mathematicians. Not at all. All right, so remember we were just talking about making a list. And then we had to make a loop in order to get all the elements of order 4. Isn't there an easier way to get a list of all the elements of order 4? Yes. So here's my list comprehension. Again, think of it as set builder notation. All the G's for G's which are elements of my group, which in this case is the Quaternion group. Well, if the order of G is 4. Okay? So I think of that as a set builder notation. And there they are. But it's in a list, right? And it's automatically in a list, and I don't have to worry about it. And now I can further process that list, or I can send that list to a friend, or whatever I want to do with it. So again, this part looks the same as it did before. All I've done is at the end, I've added this test criterion. Okay? So I have some kind of comparison, and that's the thing. This is technically called a filter. And so I've filtered out the evil elements of the Quaternion group that don't have order 4. How dare they? Right? Now, here's a nice complicated one. And I have the LaTeX for it. So let's take a look. Let's read this through. I plus j, so the set of all things that look like I plus j, for what? Let me move the cursor a little. For, well, I in the range of integers from 1 to 10, and for j in the range of integers from I to 10. Ooh, I have an error there. Can anybody see what my problem is? I have here 1 through 10 for both I and j, but that's totally wrong. So I have to fix this. Now those who weren't here last time are going to see how amazing it is that I can put LaTeX. Oops, oh, that's not where I wanted to put that, though. There we go. Less than 10, and j is between I and 10. Oops. Yeah, there's my j. All right, so it's hard to see because this is so small. Okay, I think, there we go. Great. So it's all the i's between 1 and 10, and then all the j's between I and 10. And then if I plus j is prime, so I'm notating that way, and I times j is, what's this? I plus j factorial? Not equal to, right? So this is how you say not equal to in Python. So I times j not equal to 10. Whew. And this is indeed all the sums I plus j that are prime, but where the product of I and j is not equal to 10, or that thing. I mean, this is just made up, right? I have no use for this, except that it is a nice way of demonstrating how you can be pretty complicated, and it's all one-liner. Okay? Again, when you start out, maybe you don't want to do that. But soon you're going to want to, and you want to understand other people who have written it, because you will all be looking at actual code that other people have done who didn't want to write really long loops that are kind of hard to follow. All right, how else can I create a list? So this is just more ways to make lists. There's also something called a generator. This is not as important. Oh, yes, absolutely. Questions?
In this, for I in this range, and is hidden there, and for j in this range.
I don't have to say and.
So if we have to use some or.
The and is a logical operator. So and in computer languages usually is only you comparing two truth values. Like a truth table, you know, true and true is true. True and false is false. False and false is false. But for the for, that's just it's saying do everything for I between 1 and 10. Do everything from j to 1 and 10. So even though in English speaking we would say and, in the programming language you don't have to.
If we have to like something or.
Yep, we can use or as well, but only, again, logical operators. So I could do that, and I have no idea what's going to happen there. I don't know if I'm going to get anything, actually. Maybe I'll get 7s. Oh, no, I got lots of things. Or, right, yeah. Or, right. So it's if I, what this means is I plus j is prime, or I times j isn't 10, which is almost everything. So that's what happens there. And then I could do nor, maybe. Oh, no, they don't have, it doesn't have nor built in. That's right. There's ways to do these things. But I'll stick with and for now. Does that clarify? Good. Yeah, no, it's a very good question. OK, well, this other thing is not so important, so I'll just let you know that there's a there's a way to create lists that doesn't create a list. And it's called a generator. And the reason I mention it, there's no way I would mention this if this is like actually a course for just like random undergrads. But because you guys will actually want to contribute to code, and because most of you will be probably computing quite large objects, modular forms, or huge graphs or whatever, you might not want to wait for all of them to happen right away in order to do them. So this generator object, which you can read about later on, what it does is it just says, oh yeah, I'm ready to do that. I'm ready to make a list. But it doesn't actually make the list yet. It only makes the list if you ask it to list things. So that can be very useful if you're not ready yet. Now this one is, that one's just a normal thing. You might think it makes it a tuple, but it actually makes it a generator because there's no commas. So good question. Yeah. This is not the same as a tuple. But you couldn't put commas because where would you put the comma here? It would be a syntax error. So you must just trust me that this thing makes what's called a generator object. Now I feel like I shouldn't have talked about them because I'm confusing people. But the reason I want to mention them is because it's really useful to be able to think about how they're created. So, oops. The reason why this is important is that reason. So here we go. Here is graphs 5. So the list, all graphs that are 5 vertices is a generator. It does not give you the list. That's good, because you don't want that list. It could take a long time to compute all the graphs of, what about 50? Really? Graphs 50? You want to compute all the graphs of order 50? That could take a while. In fact, let's time how long it takes to create it as opposed to how long it takes to actually list them. Now, I'm not going to list them all. I'm just going to give the length of that list. There's a difference. This is 0 seconds. This is 0.44 seconds. It actually takes a little bit of time to do that. And I've already created it too, so I didn't even, I've already, that time has already been done. So it's really useful to have this generator thing. And so you guys will want to know about that because sometimes you will want to create stuff later. But you have to be careful. You might think, oh, gee, I can use it. Huh? I won't explain this. But it's useful to know you have to be careful. And then here's all the graphs of order 4. Isn't that fun? Very cute. Okay, now, yet another data type. Okay, this one, again, not so important for random undergrad math student that I'm telling about Sage. Very important for the kinds of things that you want to do. Because most research mathematical objects are really complicated and are really easy to make mistakes on if you type them in by hand. Right? Everybody agree with that, I hope? Like a big matrix, even a small matrix. This is pretty error prone. Look at all those zeros too. Why am I typing in all these zeros for this matrix? But yet, for many matrix algebra applications in a lot of different disciplines, matrices are what we call sparse. They have very few non-zero elements. Right? There's only the zero and non-zero elements is what you care about. So instead, I'm going to try this. Okay? I'll evaluate this one just so we see the matrix. Okay? What I'm going to do is I'm going to create an object, and I'll tell you what these brackets or these braces are for in a second. And at the 1, 1 point, now what's 1, 1 in a matrix? The second column and the second row, right? So here's second column, second row. I'm going to put a 1 there. So 1, 1, colon 1. Okay? At the 2, 2, which is the third column, the third row, I'm going to put a 2. Fourth column and fourth row, I'm going to put a minus 1. So you see that that 1, 2, minus 1 corresponds to these things. Then I'm going to put them inside these curly braces. And that's called a dictionary. Curly braces with things separated by colons and commas. And I'm going to make a matrix where I plug in this dictionary thing. And I get the same one. Again, it's a harder data structure. It's okay if you're a little overwhelmed by it, but it's really useful. Because, okay, it wasn't really that much less typing here. But now imagine you have, like somebody was asking on a Sage forum this morning, a 24 by 24 matrix. Really? You want to type that all out by hand and not make mistakes? I have this problem in my research actually because, as some of you saw my colloquium yesterday, I'm doing all these voting things. So I have to write all these permutations of candidates: A, B, C, D, E, A, B, C, E, D, A, B, D, E, C. It's a lot of problem. So using this thing is really useful. And here's exactly what we do. I place things inside the curly braces. Each element of the matrix, non-zero element, was separated out by commas. And then I separated the entry location and the entry value with a colon. We call these things before the colons keys. Those are kind of like the locations. Okay? And then the things that we put in those locations we call values. So they're called keys to values. In some programming languages, these are called hash tables or something like that. But we call them dictionaries. What's that? The 0, 0 row? At the bottom.
Are you asking the order matters? Yes. It doesn't matter.
No, the order does not matter at all. So, yeah. No, if you want me to, I can totally mess this up.
Of course, it matters if you assign the same thing 2 times than the last one.
That's what we're going to see, which I didn't know until yesterday, for whatever reason. So now if I do this, I get exactly the same guy. Oh, okay. Well then.
Oh, an extra row.
That's the nice thing. I don't. I just add another one. So what do I want? For what do you want in there?
0.
Oh, okay. Well. Okay. Oh, I see what you mean because you just want another row. Yes, that's just how this matrix constructor works. Let me see if I can do this another way. Actually, there might be another way to do it. Yeah, so I can also do that. Actually, that's probably easier. Okay? Excellent question. Excellent question.
The other one is kind of cunning.
Yeah, the other one, and it's kind of stupid too, right? Because I'm putting a 0 element. That's automatic. Okay, yeah, that's a very good question, Zilpreet. Good. Excellent. Wow. Okay, so here are some subtle things about these guys. I can't put a list first because it's what's called unhashable. I'm not going to get into why that is, but you just have to be careful that you don't put things in the first spot that you're not supposed to. So usually you want like a number or a word or something like that.
You can't put a graph either.
No, you can't. Yeah, that's right. Yeah, it's too bad.
But I think you can put its incidence matrix.
You can, yeah, that's right. Well, there are some things you can put. So this thing works because it's a tuple, and tuples are hashable. Also, it's hard to add to the values. So this is something I found out the other day by a mistake in my research, actually. But Amri already knew it, so I should have just asked him. I just don't use them that often. But you can see, first I assigned 1 to 2, then I assigned 1 to 3, and the answer was, it's just going to take the last one. But in other ways, dictionaries are actually like lists, so they're not that bad. So here's a very useful one for plotting. Sage.plot.plot.plot.options is where you find all the options for plotting, default. So what's the filling opacity? How well do plots try to look at places that are very curvy? What's the thickness of a line? And is there a legend? What's the default color? And so forth. And so now let's suppose that I want all my plots to not just be straight lines. I want my plots to be dashed lines. Then I add to this dictionary. Oh, and you just use the same notation basically I use for lists. Put it in brackets. I want line style to be this string, which is dash dash. So let's evaluate it. And I get a dashed plot. It's a little hard to see because we zoomed in so much. So that's not the default in Sage. So it's very nice. And I can combine generators and dictionaries to create otherwise tedious and error-prone mathematical objects. So let's say that I wanted to make a graph of all the permutations of A, B, C, where I connect two things if and only if they share one of the things. So like here they share the B, here they share the A, here they share the C. And so I could do that by hand, or I could do this truly monstrous thing, which uses everything that we have talked about today up to this point. I use the slicing, I use the dict, I use strings, I use if, I use crazy Boolean things that you were asking about. I'm combining ors and ands and not equal tos. Then I plot it and I calculate the order of the automorphism group, which unsurprisingly is 12, since this is just going to be the dihedral group. But I'm using everything that we had up to this point. Okay, so yeah, it's pretty crazy. But the nice part is it works, and it means that I'm not typing things in by hand, and it means that if I now change this to ABCD, right? Okay, so I don't need to do this really for ABC, but for ABCD. I don't think I want to try and come up with that graph by hand. But I need to. Like, that's what I do. Well, it's not all of what I do, but it's something that I'm investigating, not this specific graph, but a closely related one. And honestly, I did it up to 5 vertices, and I think I'm kind of sick of doing them by hand now. I think 6 vertices I need to program it. Cool, right? Come on! This is amazing.
You got the same thing.
Yeah, because I went back. I changed it back to ABC. I mean, the fact that I can do this, and now, okay, you weren't impressed. Now I'll impress you, okay? You think that wasn't impressive. Let's change this to ABCDEFG. Now this could take a while. Yeah, see, you can see it's working like mad. I'm probably going to crash Amri's computer. But eventually, it's going to print it out, and it'll get the order of the automorphism group. I mean, I don't know how long it'll take to do that. I don't know. I erased it already. I'm probably going to have to interrupt this calculation, actually, because you can see it's already slowing down this little thing here. It's a bad sign. I probably asked it to do something that I should not have asked it to do. I'm going to crash. So I'm going to press the escape key, And now, so let's go back to 4. But the point is it was doing it. Okay, now we'll do this one and it'll come back. There we go. Order of the, okay, that's a pretty big automorphism. It makes sense. It's highly symmetric, right? It's a very non-typical graph, very highly symmetric graph, which is good if you're voting on these things. Okay, great. So I guess I'll even leave that. All right, so maybe we won't go over time. This is great. But is everybody with it? It's intense. It's a lot of stuff, right? So you're going to actually have to do your homework. But you're all graduate students and faculty, so you can handle it. Right, Vishwanath? Yeah, you can do it. Yeah, okay. So there's 2 more things that are just worth being aware of. Again, these are relatively advanced topics for where we are, but they're very useful for the kinds of circumstances that we are finding ourselves in as mathematicians as opposed to as students. So sometimes, these are things that are both kind of not quite what they seem. So sometimes you don't want to go to all the trouble of making a function. Making a function is a little bit tedious, and sometimes you just need a quick function. And so some programming languages have something called Lambda Functions, which apparently are related to the Lambda Functions in Lambda calculus, I guess. I don't know much about that kind of stuff. Yeah, I know. I don't, but that's what I hear, is that in the history of computer science, that's where these things came from. So we can make just a one-off function, a function which doesn't really do anything. It doesn't create a local scope for those who know what that is. And it's a very short syntax. F equals lambda x comma y colon x plus y. So I don't have to do the whole def thing. I don't have to do the indentation and all that. And it creates a function which behaves the same as a regular function. This, of course, was a pointless lambda function because I already know how to get x plus y. Okay, there's lots of ways we could have already done that. But here's a non-pointless example of why you might want a function that's just a once-off. Okay, it's just, oh, I just need a function right here, right in the middle of a list comprehension, perhaps, right? Or I might want a function in the middle of a comparison. And I don't want to have to define a whole new function and evaluate that to be able to use it in a comparison. Okay, so here's a list of points. So this is a kind of weird list of points. It's a list of integers from 0 to 9, and then sign of that integer. Not sign of pi times that integer, just a sign of that integer, which is, whatever. Okay? Dense in the unit circle, right, if you go on forever. Now, what if I want to sort these, but I want to sort them by the dependent variable? I want to sort by the values of sign, not by, it's already sorted by the value of the first thing, of I, right? But I want to sort them by the dependent variable. That's kind of hard. So there is this thing in Python called sorted. So I can sort things. But how do I sort it on the second element? That wouldn't, default sort would be lexicographical, right? So first you'd go by the first one, and then you'd go by the second element. But if I use this lambda, what I'm going to do is I'm going to sort it by the function that takes something and gives its first, so 1th element back. Right? Remember, this is the second element. So it's a function that takes something and gives me back that element. So I'm going to sort on that, on the second element. Now this is subtle, so you may have to go back and read it. But that's what's going on. It's a function that takes the list, gives you back the second element, and I'm going to sort on that. That's what this means. So if I do this, indeed, now they are sorted in order by the second element. Now, that's kind of cool, right? If you wanted to do this without a lambda, you have to create this unnecessary function. Now, of course, I called it find second element. I guess I could have called it f. I don't know. I don't find this as nice. Maybe you're not convinced. Maybe you're not convinced lambda functions are this useful based on this. Here's one where I think I can convince you. I don't know how many of you know what a Paley graph is. It's a graph that takes all elements of a prime power order field, and then it connects them with an edge if their difference is not a square in that field. Very beautiful. I have a link to the Wolfram Math World site. They have a nice article about these. And here's what I did. Okay, this is just the positioning. This is just so it looks pretty. That you can ignore that, although it's worth looking at because it uses dictionaries. But here's the part that's important. I have a graph, and what is the graph? Okay, The elements are the elements of the finite field of order 13. And the edges are, I don't know, how am I going to do this? I'm going to say edges are given by the function. Take two inputs, take two elements, and connect them by an edge if, colon, they're not the same. I don't want to make a, I want this to be a standard graph, not a multi-graph. And then if I minus j dot is square. And that's a method on finite field elements. Okay? So that's pretty cool. And of course, I can do this. I can use, you know, some other, if I want to do it for some other prime power. I have to be careful. It's not for every prime power. I think maybe it's only ones that are 1 mod 4. I have to look at the documentation for that. But I think it's really cool. And this is a place where the lambda function helps out a lot. Because otherwise, I have to write this very annoying function and then somehow put it in here. And there's no reason to do any more. It's not technically necessary, but it just speeds things up a little bit. So lambda functions. And you will see them in Sage code. Annoying corollary, I can't use lambda as a variable. So if I want to use lambda as a variable, Sage has lambda underscore. It just knows that if you do lambda underscore, it'll print properly. That's it. In case you like using lambda as a variable, you have to do this. If you don't, it doesn't matter. You can't use lambda because it's a reserved Python keyword. It's like I can't make the word def a variable because that's reserved for creating functions. But I can make e a variable. I can change e from the Euler constant to, yeah. Yes, I as well, like last time. OK, here's our final gotcha. And this is the thing. I guess we will end just about on time. There's different kinds of numbers in Sage. So here's 5 different ways to think about 2. 2 can be the integer 2. It can be the rational number 2 over 1. It can be the decimal 2.0, or real number in Sage. It can be a complex symbolic number. See, there's no decimal points. Or it can be a complex field element, like a real number, but a complex number in that sense. So not a symbolic one or integer one, but a true real number, well, complex number. You'll see what I mean when we print it out. Now that one actually is still in the symbolic ring. This, hang on. Because I have this I, and I is considered to be a symbolic element. But each of them will behave differently when you use them. And so you have to be really careful, even though these all evaluate to 2, trying to scroll back down and having trouble. And the reason is because of stuff like this. So here I have 2 1/5. I have 1/5, and I have 0.2. And Sage knows that these are the same. Or are they? B.exact rational. This is how this is actually internally represented inside of Python. Huh? Shouldn't 0.2 and 1/5 be the same? What's this thing? This is a technical but very important point about what's called floating point approximations. I'm not an expert in this, so if I say something wrong, you know, internet, don't kill me. I don't want to be flamed. But basically, in a computer, a modern computer, everything is represented as binary. So there's no way to represent, you can represent 1/5 because those are both integers, and you can represent those in binary. But you can't represent 0.2 exactly as a finite binary number. There's no expansion of 1/5 as powers of 2, or 1 over powers of 2. Now, granted, this is pretty darn close because the denominator here was 2 to the 54th. So this must be very, 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 very close to 0.2. But it's actually not the same as 0.2. And this can, again, lead to very subtle bugs if you rely on the numerical approximation of some fraction to be the same as the fraction. This even happens in, like, high school calculus or something. It certainly will occur in research mathematics. You have to be very careful to get the correct amount of precision. Now, I can ask for more precision, but even then, I can get some trouble. So here is, what I did is I created a field of 1,000 bits of precision, which is a lot of digits. And you can see here, I have printed this, and all of these digits are guaranteed to be accurate, which they are because the number is 0.2. But here's the exact rational, which has this really nasty Can you find the slash that marks where the denominator starts? Yeah, it's like right there, right? So then,
Halfway through it.
so I don't even want to know what power of 2 that is. But if you were Euler, you would have had it memorized. And you can see that if I ask for 1,010 bits of precision, uh-oh, where did that 5 come from? That shouldn't be there. But it has to be there because you can ask for arbitrary precision, but you have to ask for the precision before you ask for the numerical approximation. The 2 subtle things to end us off with today. Well, we actually made it in our allotted hour. Plenty of homework to help you practice slicing and dicing and listing and indentation and all kinds of stuff. Can you calculate sine of 1 to 1 log bits of precision? It'd be interesting to see if anybody can do that. Here's a real challenge. So this is an algebraic graph theory book. Can you do the exercises in that section? My guess is the answer is no, but if you can, I'll be really impressed. And you have all weekend, right? So anyway, so thank you very much.